Hello and welcome back to Everything Boats with Captain Frank Lanier, where we discuss boats and boating, from maintenance and repairs to seamanship and safety, as well as everything in between. This podcast is a companion to my YouTube channel of the same name, so if you like and find it useful, be sure to subscribe and please check out my YouTube channel as well, where you'll find hundreds of informative videos on pretty much every boating topic imaginable. Today's topic, solar panels. We're going to be talking about the different types of solar panels, the pros and cons for each, how to select them, how to design a system for what you're trying to do aboard your vessel, and how to install them. I first embraced the idea of solar panel while I was up a pole, literally, in the Atlantic Intercoastal Waterway. Back in the day, in the early 1980s, I was a seaman in the Coast Guard, and one of my jobs was maintaining the dayboards, buoys, beacons, all the navigation aids and stuff along the section of the ICW that I was attached to. And the Coast Guard had a massive swap out at that time. They were replacing all of their batteries, their non-rechargeable batteries, with solar power ones. And the higher ups and the Coast Guard said, well, these things will last 6 years, which was basically twice what the other batteries would last. And I was all for that because those one-shot deals, man, they were heavy, and I was a deck ape, had to lug those things up on top of these 8-ton ACE navigation. I quickly appreciated this free power from the sun thing, a concept that I continue to embrace to this day. The strategy behind solar energy on board is simple. A solar panel converts sunlight to electricity, after which wiring conducts it to your batteries for storage until needed. Solar panels are used to keep batteries or banks charged rather than power equipment directly. This arrangement allows the panel to store generator power whenever it's produced, while providing a steady source of power to a piece of equipment, even when the panel is producing no power. While they do require a little bit of initial outlay, solar panels can easily pay for themselves, and money saved and independence gained over their service life. They're noiseless, have no moving parts, and they provide free electricity for years with minimal maintenance. Solar panels also have the benefit of being modular. In other words, you can start small and you can add additional solar panels as your power requirements increase. Most any boat can benefit from solar power. Whether it's at a slip or a mooring or on a trailer, boats can keep their batteries topped off without the need for external power. You can also use solar panels to supplement or even replace other onboard charging sources, reducing or eliminate the need to run engines or generators to keep batteries topped off, which, by the way, is a wasteful practice, which not only burns fuel, but it also wears down the costliest piece of equipment on board, your engines or your generator. While underway, it's a plus to be able to recharge a dead battery in an emergency, say to operate a VHF radio or power up navigation equipment in the event of an emergency. While dockside, solar panels keep batteries charged and vital systems such as bilge pumps up and running without the need for shore power. So let's talk a little bit about the design of a solar panel. Solar panels contain photovoltaic cells, small silicone semiconductor devices that convert sunlight into electricity. Each cell generates between 0.45 and 0.5 volts, depending on exposure to direct sunlight. Cell size depends on amperage, with a 3-inch cell producing roughly 2 amps, while a 4-inch cell a little over 3 amps, and a 5-inch cell around 5 amps. Construction-wise, the three main types of solar panels are monocrystalline, polycrystalline, and amorphous or thin film technology. Monocrystalline panels have been around the longest and remain the most popular. The panels themselves are constructed of thin slices of crystal silicon. Each cell is cut from a single crystal, housed in a rigid aluminum frame and covered with tempered shatterproof glass. The panels have a uniform black, blue, or gray appearance and are generally quite rugged, although they can be cracked or broken if subjected to extreme abuse. Monocrystalline panels have the longest service life of the three types we're going to be discussing. With a conversion efficiency of about 17%, they're also the most efficient and have the highest electrical output per area of any of the panels. However, the other side, they're also the most expensive. Polycrystalline cells are sliced from a cast silicon block and have a shattered glass appearance. Built in much the same way as the monocrystalline panels, they're rectangular, giving the panel itself a tiled look. Their lifespan is similar to monocrystalline panels, and while their conversion efficiency is lower, about 14%, they're also a bit less expensive. Amorphous panels are made by placing a thin film of active silicone on a solid or flexible backing, such as stainless steel or aluminum sheeting, depending on whether the panel is to be a rigid frame and glass fronted unit or flexible. Flexible amorphous panels, in which cells are sandwiched between rubber and polymer covers, are light and tough enough that you can walk on them, and in some cases, you can even roll them up for storage. They're also better if shade is an issue. With crystalline panels, even the thin shadow of a rope or a shroud across one cell can reduce or halt output of the entire module. Amorphous panels have bypass diodes that essentially turn off shaded areas and provide a current path around them. Some monocrystalline panels also have bypass diodes, but this feature comes at an increasing cost. Amorphous panels are the least expensive of the three types. However, their efficiency is also lower, about 8%, or roughly half that of a monocrystalline type solar panel. This lower output is somewhat mitigated in newer panels, however, which use three-layer construction. And what I mean by that is each layer absorbs different colors of the solar spectrum so that the panel will deliver more power longer each day and during lower light conditions than the other two types of panels. So now let's talk about planning your system. While factors such as cost, mounting options, and output are important, a successful installation depends on knowing what you want the system to accomplish. Is the goal to float charge a single battery or supplement an overall vessel energy plan? Answering these questions up front will help determine the type, the size, and the number of panels required. To understand this process better, let's walk through the basic steps to determine power requirements and installation considerations for a single solar panel installation. In other words, this is going to be a basic system. I'll walk you through how to install it. And then you can, of course, can adjust this and increase and modify as needed, depending on the complexity of your system. For our example, the goal is to install a solar panel to provide charging for a single 12-volt, 100-amp wet cell battery used to power an automatic anchor light on a moored vessel. The first step is compiling a daily power consumption estimate to determine how much solar power is needed. The daily self-discharge rate for a wet cell battery is roughly 1%, meaning that our 100 amp hour battery requires 1 amp every 24 hours just to maintain the status quo. The anchor light draws 50 milliamps per hour of operation, and we'll assume it operates 10 hours each night. Multiplying current draw, which is 50 milliamps, by hours of daily operation, which is 10, generates a daily energy expense of 500 milliamps or 0.5 amps. This means our solar panel has to meet a minimum daily energy tab of 1.5 amps. 1 amp of battery self-discharge rate plus the 0.5 amps of power draw for the anchor light. Next up is figuring out the panel size and the best location to mount it. For our example, let's assume the panel will be a horizontal fixed mount installation. A 10-watt horizontally mounted panel should generate between 3 to 5 amp hours per day. We'll need at least 13 volts to fully charge our 12-volt battery. As most solar cells generate about 0.45 volts, you'll want a panel with a minimum of 33 cells, which should provide around 14.85 volts. Keep in mind that that's the minimum that's needed, which may not be enough once you factor in a few cloudy days. Most panels are designed to generate between 15 to 20 volts to overcome problems like cloudy days or inherent electrical resistance within the panel or your installation components. While this higher voltage lets you make up for less electrically productive days, it also means that you want to install a solar charge controller or voltage regulator to avoid battery damage during overcharging. Attempts to plan a system that utilizes the output of a panel and the capacity of the battery to prevent overcharging to avoid the installation of a charge controller is false economy and shouldn't be done. The system will never meet its full output potential, and worst case, can even damage the battery due to overcharging. So you need this charge controller to make sure that the solar panel is outputting enough, but it's not so much that it starts to overcharge and damage your batteries. So this is a good place to talk a little bit about hybrid systems and charge controller confliction. Let's say you install a hybrid system, which is at some point, you do a solar panels and you do a wind turbine.
If your boat has multiple charge sources, such as the solar panels and the wind turbine, one crucial consideration that's often overlooked is charge controller confliction. In a nutshell, charge controller confliction is an issue where the charge controller for your solar panel and the charge controller for your wind turbine are internally adjusted for the same maximum charge voltage set point. This means that they're constantly fighting each other to be the dominant power source, which results in diminished overall charging output and performance. I did a video on charge controller confliction a while back, and I will post that in the comments section, a link to that in the comments section below. So let's talk about location and mounting of your solar panel. The solar panel should be mounted in a location where they're exposed to the maximum amount of sunlight, yet they don't interfere with the operation of the vessel or movement of passengers and crew. Solar panels will typically either be fixed mounted, as our example here, or as I mentioned earlier, you can mount them on a movable bracket that allows you to actively point the panel towards the sun for maximum output. Both methods have their pros and cons. The fixed panel, which is normally mounted horizontally, doesn't produce as much power as a panel that is periodically adjusted to face the sun throughout the day, while adjustable panels have to be tended to throughout the day to fully reap the benefits of an adjustable installation. So anyway, back to our example here. After choosing and mounting the panel, it's time to connect it. The first thing you need to do is determine the size or gauge of the wiring to be used. Multiply your panel's rated amp output by 1.25, which adds a 25% safety margin. Then find the length of the entire wiring run from panel to battery and multiply it by 2. Why are you multiplying it by 2? Because you're going to each and coming back. Once you have these two numbers, refer to the American Boat and Yacht Council, ABYC's 3% voltage drop table for wire size. And there's also a handy wire calculator online for it's at the Blue Seas, I believe. I'll find it and post it in the description section below as well. For your wiring and connections, always use good quality marine grade connectors and tinned multi-strand copper wire with vinyl sheathing. This the wire will run from the solar panel to the charge controller first and then to the battery. Try to keep the wire run as short as possible, and if it transits an external deck or cabin, it likely will. Be sure to use an appropriate waterproof deck fitting so you don't have any water intrusion issues into the boat or the coring of the boat. The charge controller for the solar panel should be mounted below decks and as close to the battery as possible. You'll always want to follow the manufacturer's instructions for connections, but in a typical installation, you'll connect the solar panel's positive red wire lead to the charge controller's positive input wire or terminal, and the negative or black wire lead to the charge controller's negative input wire or terminal. Next, connect the charge controller's negative output to the battery negative terminal and the controller's positive output to the battery's positive terminal via an appropriately sized inline fuse or a circuit breaker. ABYC recommends that the fuses be installed within 7 inches of the connection to the battery or other point in the DC system. To reiterate, the installation of a charge controller can vary between modules. So the bottom line is follow the manufacturer's instructions, the installation instructions for your particular model. Finally, ensure all connections are waterproof and secure any loose wire runs with zip ties and cable clamps for a neat installation. Then get ready to lean back and soak up some free sun.
I hope you enjoyed today's podcast. And if so, and you want to buy Captain Frank a cup of coffee, please click on the support link in the text description below. All monies received, not spent on coffee, will go towards making even more awesome podcasts for my channel. And as always, thank you for your support.